welcome back. We're continuing our AP Calculus lesson in limits with limits 1.2b, algebraic limits. In the first part of this lesson, we addressed the fact that when taking a limit of a function that's continuous at a given point, we can evaluate the function at that point. Essentially, the limit as x approaches a of f of x equals f of a if f of x is continuous and defined at x equals a, or at that point. And we looked at the fact that, okay, when it's continuous, great, we can plug it in, that's direct substitution, and the value of the function equals the limit. But sometimes we would have a point discontinuity that graphically would look something like this, and we'd have this hollow point, and analytically this would be when I would have a factor in the denominator that I also had in the numerator, something that could cancel out. And when something would cancel out, that's my point discontinuity. And I would have a point discontinuity where this factor equaled 0. X plus 3 equals 0. So in this case, this would be a point discontinuity at x equals -3. And if I wanted to find what was my limit at that discontinuity, I could take my function after I canceled this out, and I could evaluate this at -3, and I get, in this case, -6 over -3 plus 1 is -2, and I would say that my limit would equal -6 over 2 is 3. But what about when I had a factor in the denominator that did not cancel out? That meant I had an asymptotic or infinite limit, and I could find the left limit or the right limit, but not a two-sided limit, because an infinite limit will never give me a real two-sided limit, because two-sided limits need to be real numbers, and infinity is not a real number. And we found that by taking what was left of my simplified function and evaluating that at a number very close. So my infinite limit here would be a discontinuity at x equals -1. That would be an infinite discontinuity at x equals -1. That's the x value that would make this 0. And then I would say, well, okay, at x equals -1, I could evaluate the simplified function at numbers very close to -1 on the left or the right to find out would I get a limit of infinity or a limit of negative infinity. For the rest of this lesson, we'll look at several other algebraic examples. Our first one here being rationalization. We'll also look at piecewise defined functions and how we can evaluate the limits of those. And then finally, we'll look at some limit laws, which are actually a really fun way to take what we know about limits and be able to combine them and find some new limits. So looking at this first lesson here, we see a rational function. And when we have rational functions meaning that they have this radical here, sometimes we can just plug it in. Always check first and see, can I do direct substitution? Check your denominator. If I were to directly substitute this 3 in here, though, 3 minus 3 would give me 0 in the denominator, and my function would be undefined. If my function would be undefined, then I need to simplify, I need to cancel. My whole goal is to cancel out that denominator. We've done factoring and canceling. Now we're going to rationalize and cancel. The rationalization that you've done primarily in the past has been rationalizing the denominator simply because proper form said we don't leave a radical in the denominator. But now we're going to rationalize the numerator because our goal is to unlock what's inside this radical so that it will simplify in order to give us an x minus 3 in the numerator that we can cancel out with this one. So what we're going to do with our rationalization here will be a little bit different than the rationalization you've done in the past, but it's the same basic principle. So to rationalize, we're going to multiply times the conjugate. And the conjugate is going to be identical to what we're trying to undo the radical of, what we're trying to rationalize. It's going to be identical, except the sign in the center will be the same. Now be careful, it's not the sign in here. It's not the sign inside the radical. That stays the same. Everything in the radical stays the same. I'm going to copy everything here over exactly the same for multiplying. So I'm going to multiply times radical x plus 1 and 2. And then I'm just going to change this sign. It was a negative, so now I'm going to have a positive in between. And I'm not trying to change the value of this function. I want to preserve its value. I'm only changing its form. So I'm going to multiply it times the exact same thing on the top and bottom. And when I do that, anything divided by itself, I always like to draw this, is 1. So I'm multiplying this function times 1, even though it's a complicated looking one. So I go to multiply, and in the numerator, I'm now dealing with binomials. So I'm foiling this. First, well, radical something times radical the exact same thing cancels out, and I get x plus 1. And that was kind of my goal. That's the whole point of this. And in fact, this is a sum and a difference. That's why I multiply times the conjugate. So I multiply the firsts, and then I multiply the lasts. 2 times 2 is 4. And when I do a sum and difference, when I multiply a sum and difference, these two would give me negative 2 times radical x plus 1. And these two would give me positive 2 times radical x plus 1. And the positive and the negative would cancel each other out. They would be gone. And all I get left is that it was negative 2 times 2, so minus 4. So my numerator is really simple, and I can even simplify this right now to x minus 3. My denominator looks a little bit more complicated, but it's actually really easy because I don't want to multiply out this x minus 3. Do not distribute that. I want to keep the x minus 3 so that eventually I can cancel it with my x minus 3 over here. So when I multiply, I'm just going to write them as two factors together that theoretically I could multiply out, but I don't want to. I want to leave them factored so that I can cancel. X minus 3 times the radical x plus 1 plus 2. And now I can cancel. These became x minus 3. I can cancel my x minus 3's out. X minus 3 was what gave me the problem with directly substituting the 3 in the first place. The moment I can cancel that x minus 3, now I can go to direct substitution. So I can rewrite this, the limit as x approaches 3. All that was left here when I canceled that out, canceling is dividing, I have 1 left. X minus 3 divided by x minus 3 is 1. And in the denominator, I have radical x plus 1 plus 2. Now I can directly substitute. I can find the value of the function at 3. And that will be 1 over radical plus 1 plus 2. Plug in my 3. 3 plus 1 is 4, and the square root of 4 equals 2. 1 over 2 plus 2 equals 1 over 4. And this is my answer. So this is my process of rationalization. Okay, so next we're going to look at a piecewise defined function, and I've gone ahead in the interest of time and filled in the equation of each piece and the constraints. We can see that we follow the function negative x minus 5. This has a slope of negative 1, up to, but not including negative 3. So that's what we see here for x is less than negative 3, but not equal to. And then my function becomes a quadratic with a vertex at negative 1, negative 6. And so we see this here. It became the opposite sign on the inside, shifted down 6. And this is from negative 3, also not included. It's not defined here at all, no equal sign. And then stops at 2. So this goes until x equals 2. And since it's defined at that point, we have our little equal sign on the less than or equal to there. And then finally, I have another linear function. This has a slope of -1/2, which we see here, and is shifted down. If I were to carry this all the way through to here, I'd see that it's shifted down 1. And this is from all values greater than 2, but not including 2 because it's hollow. When I want to find a limit, I need to pay close attention with a piecewise defined function to which side am I approaching from. The side I'm approaching from will determine which function do I evaluate. If I were finding the limit as x approached, say, -5, well, -5 fits this rule. -5 is less than -3. So I would evaluate for this piece, and I would plug -5 in here. If I were evaluating for -4 or -3.5, all of those limits would fall into this equation piece, fall into these constraints less than -3. What about the limit as x approached -3? Well, let's talk about the limit from the left. From the left means from less than, that's why we use the little negative. So the limit from the left would use this piece, and I'd plug in my -3. But the limit from the right, we can see approaching, would use this piece, the one that's greater than -3. So I would evaluate this for -3 to find my limit from the right. And then to find my two-sided limit, I would need to check. Does my left limit equal my right limit? Do they equal a real number? If so, then my two-sided limit would exist. And the same thing if I were to find the limit as x approached 2 from the left. Approaching 2 from the left from the lesser than would be here. This part has x is less than 2, so I would use this part. If I were finding as x approached 2 from the right, then I would use this part and use this function. And if I were evaluating the limit as x approached, say, 5 or 6, then those all meet greater than 2 conditions, and I would plug those values into this function. So let's look at some actual limits based on that. The limit as x approaches 2 from the right. And we're not going to look at the graph for this because we could use that to verify our answer, but we want to find out how can we determine this analytically. So the limit as x approaches +2 from the right. These are my two functions that use +2. Which one evaluates 2 from the right or from the greater than side? Well, this is the one that uses greater than. So I'm going to evaluate my function f, but I'm using this part of the function, and I'm evaluating it at x equals 2. So I take this -1/2 minus 1 and evaluate it at 2. I get -1 minus 1 is -2. Okay. How about the two-sided function of 2? Well, I know what my right side limit. How about the two-sided limit of 2? Well, I know that the right-sided limit of 2 is -2. What about the left-sided limit? So this is a little sub-step I need to do here. The limit as x approaches 2 from the left of f of x. I know again, since I'm finding the limit as x approaches 2, it has to be one of these two functions, but this time I'm approaching 2 from the left or from the lesser than. Which of these has x being less than 2? This one up here. So I'm going to use this function piece. This is going to be evaluated at x plus 1 squared minus 6. And I can evaluate this at 2 again, so it's the limit as x approaches 2. 2 plus 1 is 3 squared minus 6. 9 minus 6 equals 3. So my left-sided limit equals 3. So what is my two-sided limit? Well, my left limit is 3. My right limit is -2. For my two-sided limit to exist, my left limit must equal my right limit, must equal a real number. They do not equal each other, so my two-sided limit does not exist because my limit as x approaches 2 from the left of f of x does not equal my limit as x approaches 2 from the right of the function. Whenever our limit does not exist, we want to go ahead and take the moment and explain why. That's often important points in a question. Looking at C now, the limit of our function as we approach -3 from the left. So our function from the left of -3, these are my two functions that deal with -3. From the left is going to be the lesser than side, and this is my function that's lesser than, so I'm going to use this function. I'm finding my limit as x approaches -3, so that's what I'm going to plug into the function. -x minus 5, plug in -3, watch your signs. Negative times a negative is +3, minus 5 is -2. That's my left limit. How about my right limit? This asks for the same limit, but from the right. I'm still using one of these two functions because they're the ones that deal with -3. But this one's from the right, or from the greater than side. And now this is my function that deals with 3 is greater than -3. You can see x greater than -3. So I'm going to use this function here. X unknown plus 1 squared minus 6. I'm still evaluating for -3. -3 plus 1 is -2. Squared minus 6 is 4. Minus 6 equals -2. Okay, so question E, let's pause a second before we go to question E. Bonus question, what is the limit as x approaches -3, my two-sided limit? And you might look at the previous two-sided limit question and say, well, it's a piecewise defined function. My two-sided limit didn't exist. But that's just because in this case, the piecewise defined function gave me a different left and right limit. What about the limit as x approaches -3? Well, I look at my left limit equaled -2. And I look at my right limit also equaled -2. Therefore, my two-sided limit also equals -2 because they equal each other and they equal a real value. So we can finally look down at E, and I'm going to zoom out a bit so we can still see our piecewise defined function. The limit as x approaches -7. Now, in this case, when we try to figure out which function should I use, well, none of these functions include a 7. But I know that -7 is less than -3. That tells me it's this function. And I'm going to use my -x minus 5. -x minus 5. And I'm always evaluating at what x is approaching. So I'm going to evaluate at the -7. Watch my signs. Negative, or the opposite of -7 is +7. Minus 5 equals +2. And then the limit as x approaches -1. Again, -1 isn't explicitly mentioned here, so I want to find where would -1 fit. And -1 would lie between -3 and 2. So I'm going to use this function. And that's going to be my x plus 1 squared minus 6. And x is approaching -1, so I'm going to evaluate at -1. -1 plus 1 is 0. 0 squared is 0. Minus 6 equals -6. And that's it. Okay, so at this point, we've seen basically two main conditions where I can't use direct substitution. And 1 is when I have a fraction where a factor in the denominator could make the denominator 0, and that would cause a problem, and that could either be a point discontinuity if it cancels, or an infinite discontinuity if it doesn't cancel. This one doesn't cancel. I can also have a discontinuity that means I can't use direct substitution if I have a piecewise defined function, because I might see something that looks like this, and then I might have one function like that, and then the next function goes like this and goes like that, and I could still have my function be continuous here. We'll call this A. So I need to check with my piecewise defined functions. So we're going to have a little bit of review of these different type of limits real quick. Different types of limits. A, B, and C. Go ahead and take a moment, try those 3. Then I will display the answers, and you can either view the work for each problem that you need to see, or you can jump ahead to the next set of questions. Okay, so we'll find that the limit for each of these functions is 2. 2, 2, and 2. And you can either stick around to watch A, B, and C be worked, or you can skip down to the next set. Okay, so for A, we're finding the limit of the function g as x approaches -2. So both of these deal with -2. And then it says from the left. So I want the lesser than, this is the x is less than -2, which means I'm going to use this function here. That is going to be 2 squared plus 3 times x. And it's as x approaches -2, so that's what I'm going to evaluate in here. -2 squared is 4. 2 times 4 is 8. 3 times -2 is -6. 8 minus 6 is 2. For B, I'm finding the limit as x approaches -2, but from the right, from the greater than side. So both of these deal with -2, but this one deals with greater than -2. So I'm going to use this function, -1/2 x plus 1. And I plug in my -2 from here. -1/2 times -2 is 1. 1 plus 1 equals 2. C asks, what is my two-sided limit as x approaches -2? Well, my limit existence theorem says I need to ask, does my left limit equal my right limit? Yes. If so, do they equal a real number? Is 2 a real number? Yes. Therefore, my limit equals 2. Okay, if you like, go ahead and work any of these on your own that you feel confident trying out. The more you can practice this on your own, the more successful you're going to be. And then you can come back here and I'll present the answers and then go through each problem one at a time. Okay, here you can see the answers for A through E. Go ahead and take a moment to check your paper and see which ones you got and which ones you need to go back and review and write down the correct way to work each one. You'll see that we'll find that D is especially tricky, and we'll work through that step by step together. Okay, so we want to find the limit, and when working algebraically, first thing we're going to do is try direct substitution. And I always like to check the denominator first because that's where I can run into trouble. If the denominator would become 0, then that's a problem. So I'm actually going to start with just the denominator, and as long as that looks good, then I can do the numerator. As x approaches e means I'm going to evaluate the function for e. 2e does not equal 0. E is an irrational number equivalent to approximately 2.7. 2 times that won't give me 0. I can go ahead and fill this in up here. And that's going to be ln base e. As you may recall from your logs, the natural log base e of e is 1. and that leaves me 2e, or 1 over 2e. Okay, for b, this is asking for a limit from the left, but since this is a polynomial, it's continuous, my left limit, my right limit, they're all going to be the same. So I don't have any x's in the denominator. So I don't have any x's in the denominator. And you might say, but I have some denominator here. I have this 5, but it's a 5. And a 5 is always a 5. It's never going to be 0. As long as x isn't down there, I'm fine. So I should be able to just directly substitute this. 2/5 plus 2, and evaluate for 5. 2/5 of 5 equals 2, plus 2 times 5 is 10. Squared plus 2. Evaluate these for 5. 2/5, 5 squared is 25, plus 10. 5 and 25 reduce. 2 times 5 is 10, plus 10 equals 20. Okay, for c, I'm directly substituting pi. And since this is sine and cosine, which are continuous, there's no fractions, I should be fine. I'll go ahead and fill this out. And I'm going to rewrite this. Remember that sine squared theta is sine of theta quantity squared. And this is 2 times cosine theta. I'm going to go back and put in parentheses for my theta. And I'm going to evaluate these at pi. Okay, so sine of pi, looking at my unit circle, going around 1 pi angle, and this on my unit circle is the coordinates -1, 0, and these are labeled cosine and sine. So my sine is 0, and 0 squared is 0. And my cosine is -1. Cosine of pi is -1, and 2 times -1 is -2. 0 minus 2 is -2. Okay, so D is going to be a little bit tricky because we're substituting in a fraction here, 5 pi over 3. So I'm going to deal with a little bit of complex fraction, and I just need to watch out for that and make sure that I rearrange as I go. So directly substituting, I'm going to get tangent of 5 pi over 3 divided by 5 pi over 3 quantity squared. And it's everything there that's being squared. So let's focus on our tangent here first. 5 pi over 3 is going to be 1, 2, 3, 4, 5, which means a reference angle of pi over 3. And this is in the 4th quadrant, or the cosine quadrant. So tangent will be positive here. When I evaluate this, I'm sorry, tangent will be negative here. When I evaluate this, I'm going to take a negative value. So I can draw my reference triangle. This is my pi over 3, short side, long side, and hypotenuse. And tangent is opposite over adjacent. My opposite is radical 3. My adjacent is 1. So I can rewrite my tangent as radical 3 over 1, or radical 3. And I said that since this is in the cosine quadrant and it's tangent, those don't match, so my answer will be negative. So negative radical 3 for the numerator, divided by, this is 5 squared is 25, pi squared is pi squared, and 3 squared is 9. Now this is my big fraction, so I'm going to rewrite this complex fraction as a division of fractions. Negative radical 3 divided by this fraction. Dividing by this fraction means multiplying times its reciprocal. So times 9 over 25 pi squared. And this gives me my final answer of negative 9 radical 3 over 25 pi squared. And it's a weird answer, but it's still an accurate and correct answer. All right, so for E, we're going to go ahead and start by trying direct substitution. And I always start this with my denominator in order to find out, do I have to do more? Will my direct substitution cause me a problem? So I try to plug this in the denominator, 2 times my unknown. And we're going to evaluate at what x is approaching, negative 2. And unfortunately, this gives me negative 4 plus 4, which is a 0 in the denominator. So I'm going to kind of stop here, and I'm looking at this and I don't see any radicals, so it's not rationalization. It's just one big fraction, so it's not complex fractions. I need to factor and cancel. So I'm going to look at my numerator and factor that. It's going to be x and x. I'm going to say 2 and 3. My larger number is negative, and my signs are different. And I can also factor the denominator. I have a common factor of 2, which leaves x plus 2. And now I see that I can cancel my x plus 2's out. And remember, anytime I can cancel a factor out in the numerator and denominator, I have a point discontinuity at where this factor equals 0 or at x equals negative 2 in this case. And it's good to point that out, to mention that, write that down. This is a kind of thing that we need to be noting and recording for the AP exam. But I can take out that discontinuity, and now even though my function was undefined, I saw that here, 0 in the denominator, function is undefined, I can still find my limit because I can factor and cancel with limits. So I cancel that out, and now I evaluate what's left. Limit as x approaches negative 2 of x over 2. Negative 2 minus 3 over 2 is negative 5 over